Cesar Pereida García will present his paper, Size, Speed, and Security, and Ed25519 case study. Cesar, I think you can start whenever.
Yes, let me try share my screen. Good morning, everyone. My name is Cesar Pereida Garcia, and I'm going to present our paper, Size, Speed, and Security, an Ed25519 case study. This is work that I did while I was an intern in Huawei in Finland, in collaboration with Sampo Sovio. So this is the outline of the presentation. I'm going to talk about the background information about Ed25519. What is the case study, and a bit of analysis about the case study. Then computer-aided Ed25519 implementation, some of the results we got, and then the conclusion. So let's start with the background information. What is Ed25519 and EDDSA? So EDDSA is a elliptic curve variant of Schnorr signatures. This means that they are deterministic signatures. In other words, if we have a message and we sign it with our key, it generates always the same signature. That is different to ECDSA, where every time the signature it's different because there is some randomness involved during the signature generation. So Ed25519 was first described by Bernstein et al. About 10 years ago, and it was described as an instance of EDDSA over a twisted Edwards curve equivalent to curve 25519. So this means EDDSA is like the general umbrella term or the general algorithm, and then Ed25519 is basically EDDSA with a specific curve underneath. It provides the same security levels as NIST P256 curve, which is 2 to the 128, and is as fast as the NIST P256. So this comparison with this curve, it's important because this is probably the most widely used curve on the internet at the moment. So Ed25519 competes with this curve. But what is the need of having something that competes with P256? Well, the main benefits of EDDSA is that it provides small signatures. So there are 64-byte long signatures, uses small public keys, which are 32 bytes. And the most important and relevant, at least for this work, is that there were design choices that were made to prevent common attacks affecting, for example, ECDSA. More commonly is the non-reuse attack, and also protection against side channel analysis. So in general, this is how Ed25519 works. It is composed of 3 algorithms: key generation, signature generation, and signature verification. I think the main takeaway of this slide is that it uses 3 important operations, which is fixed point scalar multiplication, which are the ones highlighted in blue, double scalar multiplication that is used in signature verification, and scalar recoding algorithms that recode the scalar value into a different form before the scalar can be used by one of these multiplication functions. Together with the original paper, there was some reference implementation that was provided, and it's available in the SuperCub framework. So, well, actually, it wasn't only one reference implementation, but several ones. There is a basic reference implementation in C that it's slow, but it's secure and it's portable. And then there's an optimized Ref10 implementation that it's fast and also it's portable. And then there are two specific implementations. Sorry, two implementations that are specific to Intel architecture or x86 architectures, and these are even faster. But in general, all these implementations have the following requirements, or not the following requirements, but they use these different functions. So there is a double scalar multiplication function. It's called double scalar because if we go back, it performs two scalar multiplications. If you look here on the bottom, one is S times B, and the other one is the result of the hash of AM times A. So that's why it's called double scalar multiplication. This is used only for signature verification. It requires its own scalar recording algorithm and uses a very small precomputation table. On the other hand, the fixed point scalar multiplication, it's called like that because it's a scalar multiplication with a point that is known ahead of time. So by knowing ahead of time, we can pre-compute a big table that is roughly the size of 30 kilobytes. And this speeds up the computation quite a lot. This is mainly used during key generation and signature generation. And also it has its own scalar recoding algorithm. So our case study, I was handed with the task of making optimization for these reference implementations, but that would be friendly with an IoT device. So most of these devices have a very constrained memory. So because of that, the reference implementations are not possible to include in there because these are more than 100 kilobytes of size. So we had to come up with some way of optimizing it. Sometimes we can't use reference implementation or an implementation that somebody has done. So it's common to be in the case that we need to implement our own. And if we are not experienced with all the possible ways that can go wrong, then it's very likely that many things will go wrong. So a badly way to optimize for size is get rid of the thing that uses the most space, in this case, the big precomputation. So we could get rid of that at the cost of slower implementation. But if our need is a smaller size, then we must sacrifice that. And the small precomputation is really small, it's 40 bytes, so we can decide to keep it or not. Another bad optimization that we could do is to use the double scalar multiplication also as a fixed point scalar multiplication. So in our API, for example, if we only input one of the values, then we can make only one part of the double scalar multiplication. But if we input both values, then it turns into a double scalar multiplication. So by doing that, basically we're getting rid of one of the scalar multiplication functions. So we get rid of code. That makes the implementation smaller. And at the same time, we only need then one scalar recording algorithm. So that also gets rid of some code. So we end up with a smaller implementation. But I mean, this makes sense, but why is it bad? So we analyze this from a side channel attack perspective. And the basic recommendations from a sidechain analysis perspective is that we must use constant time algorithms. We have to avoid table lookups based on secrets. We have to avoid branching based on secrets, and also looping based on secrets. So taking that into account, if we look at the implementation with optimization described before, we notice that if we only have one Scalar recoding algorithm, it's very likely that the one that we use, it uses branches. So it branches on a per bit basis. This means that it checks the Scalar value, which is the secret value, bit by bit, and takes decisions based on that. That's very bad because some sidechain attacker looking either in the cache or the microarchitecture or power consumption can see if the bit was 1 or 0, and that leads to recovery of the whole Scalar value, which is the secret key. Also, it loops based on the size of the Scalar. In addition to potentially leaking the whole bits, it leaks the length of the Scalar. And in general, it's a variable time algorithm, meaning that it reveals secret information. Also, when we decided to move to one Scalar multiplication algorithm, this algorithm, it's difficult to implement in a constant time manner. So it often means that it performs table lookups based on the recorded secret Scalar. Since it's a recorded secret Scalar, it doesn't reveal bit by bit, but it reveals some of the bits of the Scalar. So that's also quite bad. And additionally, it also branches depending on some of these recorded secret Scalar. So in general, there's a lot of potential to recover secret information if we were to use this badly optimized implementation. So we end up in this situation of what do we do now? We can undo these optimizations and use the reference implementation, but that's not an option since we are trying to get something smaller. We could try to make constant time what needs to be constant time, meaning a Scalar recording algorithm in Scalar multiplication algorithms, but that's quite difficult and it requires a lot of expertise. We could use some other implementation. So there's a bunch to choose from. The reference implementations, there's the Dawn implementation, Google's Boring SSL, Monocipher is...
Cesar,
yes.
You're on the 5-minute mark.
Okay. OpenSSL, Mozilla NSS, and many more. So we decided not to go that way and instead use what is called computer-aided cryptography. For that, we use one tool that is called ECC-Kila. ECC-Kila creates portable C codes for elliptic curve cryptography. It supports different curves, among them Edward curves for ED25519, and it uses formally verified Galois field for the underlying arithmetic. And all of that is implemented in constant time. So we took ECC-Kila, we created 2 different implementations, one small implementation, one normal size implementation. The small one is roughly 40 kilobytes, the big one is 70 kilobytes, so it's even smaller than the reference implementations. And then we ran some benchmarking on SuperCub using a Raspberry Pi on different implementations. So these are the results for Intel and ARM. In general, I think what's the takeaway is that it's quite competitive, ECC-Kila, for being smaller. Of course, it's not as fast as the most fastest implementations, but it is quite competitive. for 64 bits and 32 bits. The same in ARM. In ARM, the results weren't as great as in Intel, but still it performed quite well. The conclusions is that cryptography engineering is hard, and the devil is in the details. But these computer-aided cryptographic tools, they help us to prevent common side channel flaws and other flaws. ECC-Killer is fast, secure, and produces portable code. The ED25519 implementations are around 10 years old, so there are still some improvements possible, but it will gain probably little speed based on that. From the benchmarks, monocipher, it's a good idea for a small, secure, and fast it's a good implementation for IoT devices. And on the side channel attack part, so far, there are no leaks or no attacks exploiting partial leakage on ED25519, but that's still to see. That's all for me. Thank you very much for listening, and if you have questions, please ask.
Okay, thank you, Cesar. So we have a question in the chat from Arto Niemi. What was the smallest implementation you found? How big was it? And is it secure against remote timing attacks?
I cannot see the chat from here, but so the smallest one, well, the smallest one was the one.
Do you want me to repeat the question?
I think I remember. So the smallest one was the toy example that we did here, but of course that's insecure. So that means it wasn't secure against timing attacks. But a secure one, monocipher was the smallest one, and it was roughly the same size as the ones that we generated. So it was 40 kilobytes. What was the other question?
If it is secure against remote timing attacks.
Yes. Yeah, the monocipher one, yes. But the toy example from here, no. All the reference implementations, yes, they are secure against timing attacks, remote timing attacks, yeah.
Okay. Do you have any other questions?
I can see Eugene's hand up.
Sure. Okay. Eugene, go ahead.
Cesar, your implementation of the ED25519, I think is the ECC-Killer, right?
Yes.
How easy it is to implement it, to integrate it into like an IoT board? And can you do it like bare metal, or you can apply it to like an operating system? Like, for example, Kontiki or something?
Well, I did not play with bare metal device or embedded devices, so it was a Raspberry Pi, which already has an operating system. But ECC-Killer generates C code, so I assume you could use it, and
okay.
it's quite easy to use. In this case, ECC-Killer does not produce the whole ED25519, so it produced the underlying layers of arithmetic, and then on top of it, we had to implement 3 or 4 algorithms specific to this ED25519. But if you use something that is supported by ECC-Killer, then it's just press one button and it generates the whole stack.
Okay, the reason I'm asking is I did some work using ED25519, and I realized that the scalar multiplication was one of the most expensive computations, which took like 3 seconds on a very resource constrained device, like 10 kilobit memory. So
Yeah.
I was wondering if the ECC cloud could do better, or if or could be an alternative to such stuff.
That's a very constrained device, I have to say, but yeah, I think you would need to try it. It is fast, but for such a constrained device, I don't know if it could do much better. To be honest, you would need to try it.
All right, sure. Thank you.
No problem.
Okay, so we're out of time for questions. So if you want to ask anything else, you can add, send Cesar something in the chat or reach him by email.